Scheduler is a kernel function that makes a decision on whether it executes the current process continuously or switch to the other process. Scheduler is activated depending upon whether a operating system takes cooperative approach or uncooperative approach in scheduling the processes. For example, here this is timeline, and then let's assume that we take the cooperative approach. Then system call is called here, for example, I yield. And then at this point, the control is transferred from the user to the kernel. And then when the control is transferred to kernel, kernel runs the scheduler at this point to check how long the process has been executing and it is necessary to switch to CPU to other processes. And if it decides to let the current process to run continuously, then it returns, and then it keeps going. And then sometimes later, if the system calls user process called system call read, then operating system takes control and run the scheduler again. This is the execution of a scheduler in the cooperative scheduling paradigm. In uncooperative scheduling paradigm, user process is interrupted every so often periodically. Say this is timer interrupt, another timer interrupt, and another timer interrupt. In this case, every time timer interrupt is triggered, the operating system has to react to the timer interrupt, so it triggers timer interrupt handler. At this point, this is user, and this is kernel. The user executing and timer interrupt is triggered, so the control is transferred to the kernel, and here it triggers timer interrupt handler, and also it triggers the scheduler. And at the scheduler, the kernel computes how long the process has been executing, and it determines whether it continues to execute the prime process, or it decides to or switch to another process. If the scheduler decides to run another process, then operating system has to execute context switch. Context switch is an act of switching the context. There is CPU. And CPU has registers in it. This is register 1, register 2, for example. Okay, so there is process 1, and it contains memory. And there is a process 2, and it contains also memory. When a context switch happens, the scheduler has to save the current register values of the currently running process to somewhere in the address region of the process 1. And then it has to load the register values process 2 from its memory to the current register profile of the CPU. Like this. So it saved the register values of the currently running process to the address space of the P1, and then it restored the register values from the stack somewhere in memory region of the process to the registers. So it is called context switch. And then there is important register ESP. This is stack pointer. And stack pointer points to the top of the stack of the currently running process. As a last step to do context switch, it has to switch the value of ESP from pointing to the stack top of the process 1 to the value of stack top to the process 2. So that are the 3 steps associated with context switch. Let me explain the details of execution flow under limited direct execution protocol with timer interrupt. When the system starts, the timer starts. So the timer interrupts CPU in every X milliseconds. Process A is executing, and then assume that timer interrupt has raised. Then when the operating system receives timer interrupt, it saves the registers to the kernel stack of process A. It is important that registers are stored at the kernel stack. And then it moves to the kernel mode, and then it executes a trap handler. Trap handler corresponds to the interrupt handler for timer interrupt. And then it is executed. The scheduler decides to switch the process from process A to process B. And then it calls switch routine. And then it saves the register to the proc structure of A. And then it restores the register B from the proc structure of B to the register. And then it switches the stack top pointer A. It points to the kernel stack of B. And then it returns from trap. Then when it returning to the trap, it restores the register from the kernel stack of B, and then it starts jump to the B's program counter, and then process B starts. This is the detailed steps of context switch in the operating system called XV6. So it pushes the register values to the kernel stack of the current process, and then it loads the new registers from the kernel stack of the next process to run. What happens if during the interrupt or trap handling another interrupt happens? It may entail a race condition. The operating system usually disables interrupt during interrupt processing, and there is a sophisticated locking mechanism to protect the concurrent access to the internal data structures.